What is heat, really? The dance of excited molecules and a gentle journey through the hidden world of energy. Hello there, my wonderfully curious friends. Welcome to another evening journey into the fascinating realm of science, where we'll explore questions that have puzzled and delighted human minds for centuries. As you settle into your favorite listening spot, perhaps tucked under soft blankets, maybe gazing out at the stars or simply letting your mind wander, in that perfect twilight space between wakefulness and dreams, I'm genuinely curious about where in this vast world you're joining me from tonight. Are you listening from a cozy bedroom in bustling Tokyo, where the city lights twinkle like earthbound constellations? Perhaps you're in a quiet countryside cottage in Ireland, where the evening mist is just beginning to settle over emerald fields. Maybe you're in sunny California, where the day's warmth still lingers in the air, or in snowy Minnesota, where winter's crisp breath paints delicate frost patterns on your windows. Wherever you are, I wonder, what time is it in your corner of the world? Is it that magical golden hour when day slowly surrenders to night? Or perhaps it's already deep into evening, when darkness wraps around us like a gentle embrace. Tonight, we're going to embark on a particularly enchanting exploration, one that touches every single moment of your existence, yet remains beautifully hidden from our everyday awareness. We're going to discover the secret life of heat, not just what it feels like when you wrap your hands around a warm mug of cocoa or step into sunshine after a cool morning, but what heat truly is at its most fundamental level. We'll uncover the invisible dance that's happening right now in every atom of your body, in the air around you, in the walls of your room, and indeed in every single thing that exists in our universe. This is a story about motion so tiny and so rapid that it exists entirely beyond the reach of our senses, yet it shapes every experience we have. It's a tale of particles jiggling and bouncing and spinning in an endless, joyful celebration of energy that began with the very birth of the universe itself. Tonight, we'll discover that what we call heat isn't actually a thing at all, but rather a process, a magnificent molecular ballet that connects the morning coffee, warming your hands, to the nuclear fusion occurring in the heart of distant stars. Before we begin this gentle journey together, I'd love to invite you to show your appreciation for these evening explorations by tapping that like button if you're finding these bedtime science stories helpful for your wind-down routine. And if you'd like to join our growing community of curious minds who enjoy falling asleep to the wonders of the universe, consider subscribing for more gentle adventures into the fascinating world around us. I should probably offer you a fair warning, though. Tonight's topic is so surprisingly captivating that you might find yourself too interested to fall asleep immediately. We'll be discovering that the simple act of feeling warmth connects you to cosmic history, that every breath you take involves a symphony of molecular movements, and that the difference between hot and cold is far more beautiful and strange than you might ever have imagined. If you find your mind too engaged to drift off, simply let the words wash over you like gentle waves, knowing that the wonder will still be there when you revisit this journey another evening. So let's take a gentle stroll together through the hidden landscape of heat, where we'll meet dancing molecules, explore the birth of our understanding of energy, and perhaps discover that the universe is far more alive and dynamic than we ever suspected. Are you ready to uncover the secret life of the world around you? Imagine for a moment that you could shrink yourself down to an impossibly small size, smaller than the tiniest grain of sand, smaller than the most minute speck of dust, smaller even than the wavelength of visible light itself. Picture yourself becoming so microscopically small that you could actually see individual molecules, those infinitesimally tiny building blocks that make up everything around you. What do you think you would discover in this invisible realm? If you were to peer into this molecular world right now, even as you lie perfectly still listening to these words, you would witness one of the most astounding spectacles in all of nature. Every single molecule around you, in the air you're breathing, in the pillow supporting your head, in the device playing this audio, even in your own body, would appear to be in constant, frenzied motion. Not just gentle swaying or slow drifting, but rapid, chaotic dancing that never, ever stops. The oxygen molecules entering your lungs right now are careening about at an average speed of roughly 1,000 miles per hour. That's faster than the speed of sound, faster than a jet aircraft. And they're not moving in straight lines. They're bouncing off each other, spinning, tumbling, colliding in a cosmic dance that has been going on since the moment these atoms first came together billions of years ago. This invisible dance of molecules is what we call heat. It's such a beautifully simple concept, yet it revolutionized our understanding of the universe when scientists first grasped it fully in the 19th century. Heat isn't a substance that flows from hot objects to cold ones, as people believed for thousands of years. Heat isn't some mysterious fluid or essence. Heat is simply the motion of molecules, their kinetic energy, their joyful, ceaseless movement through space. When you feel the warmth of sunshine on your face, what you're actually experiencing is the result of sunlight energizing the molecules in your skin, causing them to dance faster and more vigorously. When you step from a warm room into cool evening air, the molecules in your skin are gradually slowing their dance, releasing their excess energy to the slower-moving molecules in the surrounding air. Let's imagine this together. Picture a crowded dance floor at a lively celebration. Some dancers are moving energetically, bouncing and spinning with enthusiasm. Others are swaying more gently to the rhythm. Now imagine that the energetic dancers occasionally bump into the gentler ones, and when they do, some of their energy transfers over. The gentle dancers start moving a bit more vibrantly, while the energetic ones settle into a slightly calmer rhythm. This is exactly what happens when hot objects cool down and cool objects warm up. It's simply energy transferring through molecular collisions. But here's where it becomes truly magical. This dance is happening at every scale, in every corner of existence. Right now, as you listen to these words, the iron atoms in your blood are vibrating about their positions in hemoglobin molecules. The calcium atoms in your bones are oscillating in tiny, regular patterns. The water molecules that make up roughly 60% of your body are in constant motion, creating the very warmth that maintains your life. And this isn't just happening inside living things. The aluminum atoms in a distant airplane wing flying overhead are dancing. The silicon atoms in mountain rocks are gently vibrating. Even the carbon atoms in diamonds, locked in that incredibly strong crystalline structure, are in perpetual motion. The entire universe is alive with this molecular choreography. The faster these molecules move, the more heat energy they contain, and the hotter we perceive the object to be. The slower they move, the less heat energy they possess, and the cooler the object feels. This relationship is so fundamental that it defines one of the most important concepts in all of physics: temperature. Temperature, you see, is really just the average kinetic energy of all those dancing molecules. When we say something is hot, we're saying its molecules are, on average, moving very quickly. When we say something is cold, we're describing relatively slow molecular motion. And here's a fascinating thought. There's actually a theoretical point where molecular motion would come to a complete stop. Scientists call this absolute zero, minus 459.67 degrees Fahrenheit, or minus 273.15 degrees Celsius. At this temperature, the molecular dance would cease entirely, and no heat energy would remain. Of course, absolute zero is impossible to reach in practice, and perhaps that's for the best. A universe without molecular motion would be a universe without heat, without life, without the dynamic processes that make existence possible. Even in the coldest depths of outer space, far from any star's warmth, molecules still maintain a tiny amount of motion, still participate in the cosmic dance that has been ongoing since the Big Bang itself. Consider this remarkable fact. The heat in your body right now represents a direct continuation of energy that has been flowing and transforming since the universe began. The molecular motion generating your body warmth connects you to the primordial fires of stellar formation, to the nuclear furnaces, burning in distant suns, to the gradual cooling and heating cycles that have shaped our planet for billions of years. When you touch something warm, you're not just feeling heat, you're sensing the echo of cosmic history. You're experiencing the result of countless energy transformations that stretch back through deep time to the very birth of matter itself. Every warm sensation is a reminder that you are intimately connected to the grand energetic processes of the universe. But let's bring this cosmic perspective down to a more intimate scale. Think about the last time you held a cup of hot tea or coffee. As you wrapped your hands around that ceramic mug, the faster-moving molecules in the hot liquid were bumping into the molecules in the ceramic, causing them to dance more vigorously. These ceramic molecules then collided with molecules in your skin, transferring some of their kinetic energy to your nerve endings. Your nervous system interpreted this increased molecular motion as warmth, and you experienced that lovely sensation of heat flowing into your palms. This simple exchange, hot tea warming your hands, represents the same fundamental process that powers stars, drives weather patterns, enables life itself, and shapes the structure of galaxies. It's all molecular motion, all kinetic energy flowing from places where molecules are dancing rapidly to places where they're moving more slowly. And here's perhaps the most beautiful part of this invisible dance. It's happening right now, all around you and within you, creating the very conditions that make consciousness possible. The warmth of your body, the air filling your lungs, the gentle heat radiating from any electronic device nearby. All of these represent countless trillions of molecules participating in an ancient dance that connects this moment to the deepest mysteries of existence. As you settle more comfortably into your listening space, take a moment to marvel at this hidden choreography. Feel the warmth where your body touches your blankets or pillow. Sense the temperature of the air entering your nostrils. Notice any warm or cool sensations on your skin. You're not just experiencing physical comfort, you're feeling the direct effects of a molecular dance that has been continuous for nearly 14 billion years, a dance that connects your immediate sensory experience to the fundamental forces that built and sustain our universe. As we continue our gentle exploration of the invisible world of molecular motion, let's pause to consider a fascinating confusion that puzzled brilliant minds for centuries. It's a distinction so subtle yet so important that understanding it opens up entire new ways of seeing the world around us. We're going to discover the elegant difference between heat and temperature, two concepts that seem similar but are actually as different as a rushing river and the speed of its current. Imagine, if you will, two swimming pools on a quiet summer evening. The first is a large Olympic-sized pool, vast and deep, filled with thousands upon thousands of gallons of water. The second is a charming hot tub, small and intimate, designed for just a few people to relax together. Now, picture that both bodies of water are at exactly the same temperature. Let's say a perfectly comfortable 80 degrees Fahrenheit. If you were to dip your toe into each one, they would feel identical. Your skin couldn't tell the difference because the average molecular motion in both pools is exactly the same. The water molecules in both the large pool and the small hot tub are dancing at precisely the same average speed. This is what temperature measures, the average kinetic energy of molecules, their typical speed of motion. But here's where it becomes fascinating. Although both pools feel the same to your toe, they contain vastly different amounts of heat. The large pool, with its tremendous volume of water, contains hundreds of times more total molecular motion, more total kinetic energy, more heat than the small hot tub. It's like comparing a gentle breeze that spans an entire continent to a gentle breeze in your backyard. They feel the same, but one involves incomparably more air molecules moving at that same speed. This distinction between heat and temperature is one of the most elegant concepts in all of science, and it explains so many mysteries that you encounter in daily life. Have you ever wondered why a small campfire flame, which might be 1000 degrees Fahrenheit, can't warm a large room as effectively as a much cooler wood stove at only 500 degrees? The flame has a higher temperature, its molecules are dancing faster, but the wood stove contains much more total heat energy, much more total molecular motion. Let's imagine this concept through a beautiful metaphor. Picture temperature as the intensity of joy at a celebration. Some gatherings might have incredibly enthusiastic people, high intensity, high temperature. But a small group of very enthusiastic people might have less total joy in the room than a large group of moderately enthusiastic people. Heat is like the total amount of joy in the room, while temperature is like the average intensity of individual happiness. This understanding revolutionized how we think about energy in the 18th and 19th centuries. Before scientists grasped this distinction, they believed heat was a mysterious substance called caloric that flowed from hot objects to cold ones like an invisible fluid. They thought hot objects contained more of this caloric substance and cold objects contained less. But this couldn't explain why rubbing two sticks together could create seemingly endless amounts of heat, or why mechanical work could be converted into warmth. The breakthrough came when brilliant minds like Count Rumford and James Prescott Joule realized that heat and mechanical motion were intimately related. Joule, in particular, conducted beautiful experiments where he used falling weights to turn paddles in water, showing that mechanical energy could be precisely converted into heat energy. He was literally watching mechanical motion being transformed into molecular motion, seeing the connection between the visible movement of his apparatus and the invisible movement of water molecules. Consider the implications of this understanding for your own daily experience. When you rub your hands together vigorously on a cold day, you're converting the macroscopic motion of your palms into microscopic motion of the molecules in your skin. The organized movement of your hands transforms into the disorganized, chaotic motion of countless tiny particles, creating warmth. You're literally conducting a molecular orchestra, turning coordinated motion into beautiful, warming chaos. Or think about what happens when you exercise. Your muscles are converting chemical energy from food into mechanical motion, but in the process, much of that energy becomes heat, increased molecular motion throughout your body. This is why physical activity makes you warm, why your body temperature rises during a workout. You're essentially operating an incredibly sophisticated engine that transforms stored chemical energy into motion and heat. The relationship between heat and temperature also explains some wonderfully counterintuitive phenomena. Have you ever noticed how massive objects like stones or concrete retain warmth long after the sun has set, while lightweight objects like aluminum foil cool down almost immediately? This happens because the massive objects contain many more molecules, so even though their temperature might be the same as lighter objects at any given moment, they contain much more total heat energy. They have more molecular motion to give up as they cool down. This principle governs everything from how your body maintains its temperature to how our planet's climate systems work. Your body is constantly managing both heat and temperature, using its massive thermal capacity, all those trillions of molecules in bones and organs and blood, to maintain a steady temperature even as heat flows in and out through your skin. Earth's oceans work similarly, storing vast amounts of heat that help stabilize our planet's temperature despite the changing seasons and varying amounts of solar energy we receive. Let's take a gentle stroll through another beautiful example. Consider what happens when you pour hot coffee into a cold ceramic mug. Initially, the coffee has both high temperature and substantial heat content. Its molecules are moving rapidly, and there are many of them. The ceramic mug starts with lower temperature and much less heat content. But as molecular collisions transfer energy from the coffee to the mug, something elegant occurs. The coffee gradually loses some of its molecular motion, its temperature dropping, but that energy doesn't disappear. It flows into the ceramic, causing those molecules to dance more vigorously. Eventually, both the coffee and the mug reach the same temperature, the same average molecular motion. But during this process, the total amount of heat energy, the total molecular motion in the combined system, remains constant. Energy has flowed, but none has been lost. It's simply redistributed from one set of dancing molecules to another. This conservation of energy, this understanding that heat is simply molecular motion that can be transferred but never destroyed, represents one of the most profound insights in human knowledge. It tells us that the universe operates according to precise, mathematical relationships that connect the smallest molecular movements to the largest cosmic processes. Even more remarkably, this relationship between heat and temperature helps us understand how life itself is possible. Living organisms are essentially sophisticated heat engines, constantly converting energy from one form to another while maintaining the precise temperatures necessary for biological processes. We extract chemical energy from food, transform it into mechanical motion in our muscles, electrical signals in our nerves, and heat that maintains our body temperature. We are walking, thinking examples of thermodynamics in action. As you rest there listening to these words, your body is performing countless energy transformations every second. Chemical reactions in your cells are releasing energy that becomes molecular motion, maintaining the warmth necessary for consciousness itself. Your brain, consuming about 20% of your body's total energy, is a remarkable engine that converts chemical fuel into the electrical and thermal activity that creates thoughts, memories, and awareness. And all of this activity, from the cosmic dance of molecules in distant stars to the intimate biochemical processes maintaining your body temperature right now, follows the same fundamental principles. Energy flows from regions of higher molecular motion to regions of lower molecular motion. Heat seeks equilibrium, always moving from hot to cold, from fast-dancing molecules to slower-dancing ones. But this flow doesn't just create equilibrium, it creates the dynamic processes that make complex phenomena possible. The temperature differences between your warm body and the cooler air around you drive the heat transfer that helps regulate your metabolism. The temperature differences in Earth's atmosphere drive weather patterns that distribute moisture and nutrients across the planet. The temperature differences between the hot cores of stars and the cold depths of space drive the nuclear fusion that creates the very elements from which life is built. In this gentle evening light, as your body gradually relaxes and your thoughts begin to slow, remember that you are participating in this cosmic flow of energy. The warmth you feel, the comfort of your body temperature, the gentle heat radiating from your skin into the air around you, all of these represent your intimate connection to the fundamental processes that govern reality itself. You are not separate from the dance of energy that shapes the universe. You are part of it, a temporary, beautiful organization of molecules whose motion creates the warmth, the consciousness, the very experience of being alive and aware in this extraordinary cosmos. Now that we've explored the beautiful secret that heat is simply molecular motion, and we've distinguished between the intensity of this motion and its total amount, let's embark on a gentle journey to discover how this energy travels through our world. Like water finding its way from mountain peaks to the sea, heat energy has its own pathways, its own preferred routes for traveling from places where molecules dance rapidly to places where they move more slowly. There are three primary ways that heat makes these journeys. Three fundamental pathways that govern everything from why your coffee cools down to how our sun's energy reaches Earth to warm your face on a spring morning. Each pathway has its own personality, its own elegant mechanisms, and its own role in the grand symphony of energy that shapes our universe. Let's begin with the most intimate and direct pathway, conduction. Imagine yourself walking barefoot across different surfaces on a quiet morning. First, you step onto cool tile flooring, and immediately you feel that characteristic chill against your skin. Then you move to a wooden floor at the same temperature, and somehow it feels warmer, more comfortable. Finally, you step onto a plush carpet, and your feet feel almost cozy, despite all three surfaces being at exactly the same temperature according to a thermometer. This fascinating difference in sensation reveals the beautiful world of thermal conduction. When your warm foot touches the cool tile, heat energy immediately begins flowing from the faster-moving molecules in your skin to the slower-moving molecules in the ceramic. Tile is an excellent conductor of heat, meaning its molecules are very good at passing energy along from one to another, like enthusiastic dancers bumping into their neighbors and spreading the rhythm throughout a crowd. The tile molecules, once energized by the heat from your foot, quickly share this energy with their neighboring molecules deeper in the material. This creates a continuous pathway for heat to flow away from your skin, making the tile feel cold even though it's actually warming up from your body heat. It's such an efficient process that your foot can't warm the surface faster than the energy flows away, so it continues feeling cool against your skin. Wood, on the other hand, is a more modest conductor of heat. Its molecules don't pass energy along quite as enthusiastically, so heat from your foot doesn't flow away as rapidly. The surface can warm up slightly from your body heat, creating a more comfortable sensation, and carpet, with its fibers full of tiny air pockets, is an even gentler conductor, allowing the surface to warm quickly and providing that cozy feeling against your skin. This principle of conduction governs so many of the thermal experiences in your daily life. When you touch a metal spoon that's been sitting in hot soup, the rapid molecular collisions along the length of the metal transfer energy from the hot end to the cool end almost instantly. The molecules in the metal are packed closely together and can efficiently bump into each other, creating a highway for thermal energy to travel. But conduction requires matter, requires molecules that can physically collide with each other to pass energy along. So how does the sun's warmth reach us across 93 million miles of empty space? How does energy travel through the vacuum where there are no molecules to conduct heat? This brings us to the second pathway, Radiation. Electromagnetic radiation is perhaps the most mysterious and beautiful of heat's traveling methods. Unlike conduction, which requires direct molecular contact, radiation can carry energy through completely empty space. It's the pathway that brings warmth from every star in the universe, that allows campfires to warm your face from across a clearing, that enables heat lamps to provide comfort in outdoor restaurants on cool evenings. Every object that contains any heat at all, which means every object in the universe warmer than absolute zero, is constantly emitting electromagnetic radiation. Right now, your own body is glowing, sending out infrared radiation in all directions. You can't see this glow with your eyes, but it's there. A constant stream of electromagnetic energy radiating away from your skin. This invisible light carries away some of your body's heat energy, which is why you eventually feel cool in a cold room, even if you're not touching anything cold. You're literally shining your heat energy into the surrounding space through electromagnetic radiation. If you could see an infrared light, you would appear as a glowing human-shaped beacon in the darkness, warmer at your core and cooler at your extremities, a beautiful map of your body's heat distribution. The sun, of course, is the ultimate radiative heater in our solar system. Nuclear fusion in its core creates temperatures of millions of degrees, causing its surface to emit tremendous amounts of electromagnetic radiation across many frequencies. Some of this radiation is visible light that illuminates our world, but much of it is infrared radiation that we experience as warmth. This energy travels through the vacuum of space at the speed of light, taking about 8 minutes to journey from the sun's surface to your skin. When this solar radiation strikes your body on a sunny day, the electromagnetic waves are absorbed by molecules in your skin, causing them to vibrate more rapidly. The radiant energy transforms directly into molecular motion, into heat, without any need for physical contact. It's an almost magical process. Energy that began in the nuclear fires of a star 93 million miles away becomes the warmth you feel on your face. But radiation does something particularly elegant. It allows objects to both emit and absorb thermal energy simultaneously. On a clear night, you can actually feel cool radiation from the vast, cold depths of space. Your body, being warmer than the cosmic background, radiates more energy into space than it receives back, creating a gentle cooling effect. This is why clear nights often feel cooler than cloudy nights at the same air temperature. Clouds reflect some of your radiated heat back to you, while clear skies allow it to escape into the cosmos. Now, let's explore the third pathway, one that creates some of the most dynamic and beautiful heat transfer processes in our world: convection. Convection is heat transport through the bulk movement of fluids, liquids and gases that can flow and circulate. Unlike conduction, where heat moves through matter, but the matter itself stays in place, convection actually carries heated material from one location to another. It's the process that creates ocean currents, drives weather patterns, enables flight, and allows your radiator to warm an entire room. Picture a pot of water slowly heating on a stove. As the water at the bottom warms up, its molecules begin dancing more vigorously, and something beautiful happens. The water expands slightly, becoming less dense than the cooler water above it. Like a bubble of air rising through heavier liquid, this warmer, lighter water begins to rise toward the surface. As the heated water rises, cooler, denser water flows down to take its place near the heat source. This creates circulation patterns, elegant loops of flowing water that continuously transport heat from the bottom of the pot to the surface. You can actually see this process if you add a few drops of food coloring to the water. Colored streams will rise and fall in mesmerizing patterns, revealing the invisible currents that carry thermal energy throughout the liquid. This same principle operates in your home's heating system. When air near a heat source warms up, it expands and becomes less dense, causing it to rise. Cooler air flows in to replace it, creating circulation patterns that distribute warmth throughout the room. The heated air carries its molecular motion with it as it moves, physically transporting thermal energy from one location to another. Convection creates some of the most spectacular phenomena in our natural world. The great ocean currents that regulate Earth's climate are massive convection systems, with warm water from tropical regions flowing toward the poles, while cold water from polar regions flows toward the equator. These currents transport enormous amounts of heat energy across our planet, moderating temperatures, and creating the conditions that make life possible in many regions. Weather systems are essentially atmospheric convection in action. When the sun heats land surfaces during the day, the air above them warms and rises, creating areas of low pressure. Cooler air flows in to replace the rising warm air, creating winds. Clouds form when warm, moisture-laden air rises and cools. Thunderstorms develop when convection becomes particularly vigorous, with powerful updrafts and downdrafts, creating the dramatic displays of energy we see during summer storms. Even your own body uses convection to help regulate temperature. Your circulatory system is an intricate network of convective heat transfer, with warm blood from your core flowing to your extremities and cooler blood returning to be reheated. When you're too warm, blood vessels near your skin dilate, allowing more heated blood to flow close to the surface where convection and radiation can carry away excess heat. When you're cold, these same vessels constrict, keeping warm blood closer to your vital organs. Let's imagine these three pathways working together in a simple scene that you might experience any evening. Picture yourself sitting near a fireplace on a cool night. The burning wood creates hot gases and glowing coals at very high temperatures. Heat travels from these hot materials to your body through all three pathways simultaneously. Conduction carries heat through the air itself. Though air is not a particularly good conductor, the molecules nearest the fire do bump into slightly more distant molecules, creating a weak but measurable flow of thermal energy outward from the flames. If you place your hand near a warm stone hearth, conduction through the solid rock brings heat from the fire's location to the surface where you can feel it. Radiation streams outward from the glowing coals and flames in all directions. This electromagnetic energy travels at the speed of light directly to your skin, where it's absorbed and converted back into molecular motion. You can feel this radiant heat immediately when you face the fire, and you notice its absence immediately when someone walks between you and the flames, blocking the radiation. Convection creates the gentle air currents you feel near the fireplace. Hot air rises from the flames, creating a circulation pattern that draws cooler air from the room toward the fire. This moving air carries some heat with it, and if you position yourself in these convection currents, you feel additional warmth beyond what radiation alone provides. All three processes work together to create the total warming effect, each contributing its own character to the experience. The radiant heat provides immediate warmth when you face the fire. The convective currents create gentle air movement and help distribute heat throughout the room. The conductive heat through the hearth provides a steady, continuous warmth that persists even after the flames die down. Understanding these three pathways helps explain so many thermal mysteries in daily life. Why does a metal park bench feel colder than a wooden one on the same winter day? Superior conduction in the metal. Why do you feel warm when you face a sunny window, even if the air temperature is cool? Radiant heat transfer. Why does a ceiling fan help you feel cooler in summer, even though it doesn't actually lower the air temperature? Enhanced convective heat transfer from your skin. These same three processes that govern your comfort around a fireplace also operate at cosmic scales. Stars transfer energy through radiation across vast distances. Planetary atmospheres circulate through massive convection systems. Rocky planets conduct heat from their molten cores toward their surfaces. The entire universe is shaped by these fundamental pathways of energy transport. As you settle deeper into your evening rest, take a moment to notice these processes at work around you. Feel the conductive exchange where your body touches your bedding. Sense any air currents that might be carrying heat through convection. Notice the radiant heat from any warm objects nearby, or perhaps the subtle cooling effect of radiation to cold windows or walls. You're experiencing the same fundamental processes that drive weather patterns, ocean currents, stellar evolution, and the heat engines that power all life on Earth. In your immediate, intimate experience of warmth and cooling, you're connected to the grand energy flows that shape our entire cosmos. As we continue our gentle journey through the invisible world of heat, let's take a contemplative stroll backward through time to explore one of the most fascinating stories in the history of human understanding. For thousands of years, brilliant minds grappled with a mystery that surrounded them every moment of their lives. What exactly is this phenomenon we call heat? Where does it come from? How does it move? Why do some things stay warm while others grow cold? The story of how we came to understand heat is really a story about the nature of scientific discovery itself. How? Human curiosity, careful observation, and elegant experimentation can gradually illuminate truths that were hidden in plain sight for millennia. Picture yourself in ancient Greece, walking through the Agora in Athens on a warm afternoon around 400 BCE. The great philosophers of the time, Aristotle, Democritus, and others, are pondering the fundamental nature of reality. They've proposed that everything is made of four basic elements: earth, water, air, and fire. In this view, heat is simply the manifestation of the fire element within objects. Hot things contain more fire essence, cold things contain less. It's an elegant, intuitive explanation that feels almost poetic in its simplicity. This idea that heat is a substance, something that can be contained within objects, dominated human thinking for over 2,000 years. It felt so obviously correct. After all, when you warm your hands by a fire, it certainly seems like something is flowing from the flames into your skin. When you heat a piece of metal, it seems to absorb and store some kind of warming essence. When that metal cools down, it appears to release that same essence back into the surrounding air. By the 18th century, this ancient intuition had evolved into a sophisticated scientific theory. Brilliant researchers like Antoine Lavoisier had refined the concept into what they called caloric theory. Caloric was imagined as an actual substance, invisible, weightless, but nonetheless real, that flowed from hot objects to cold ones, like water flowing from a high reservoir to a low one. According to caloric theory, every object contained a certain amount of this mysterious fluid. When you rubbed two sticks together to start a fire, you were somehow squeezing caloric out of the wood, concentrating it until it became visible as flame. When you mixed hot water with cold water, caloric flowed from the hot water to the cold water until both reached the same temperature. It was a beautifully logical framework that seemed to explain almost every thermal phenomenon that 18th century scientists could observe. But let's imagine ourselves in Bavaria in 1798, in the workshop of Count Rumford, a fascinating character who was both scientist and adventurer. Rumford had been tasked with overseeing the boring of cannons for the Bavarian army, and he noticed something that troubled the caloric theory deeply. As the boring tools cut into the metal, tremendous amounts of heat were generated, so much heat that water used to cool the process would actually boil. Now, according to caloric theory, this heat should have come from caloric stored in the metal. But Rumford observed something remarkable. The duller the boring tool became, the more heat was produced, not less. And the process seemed capable of producing unlimited amounts of heat as long as the mechanical work continued. Where was all this caloric coming from? The metal wasn't getting lighter, so the caloric wasn't coming from some internal store. Something fundamental was wrong with the prevailing understanding. Rumford proposed a radical idea. What if heat wasn't a substance at all, but rather a form of motion? What if the mechanical action of boring was somehow being converted directly into heat? This was a revolutionary thought that challenged everything scientists believed about the nature of thermal energy. But the scientific community wasn't ready for such a dramatic paradigm shift. Caloric theory worked too well in too many situations to be abandoned based on one puzzling observation. It would take decades more of careful experimentation and theoretical development before the true nature of heat became clear. Let's travel forward to the 1840s and meet James Prescott Joule, a British physicist whose meticulous experiments would finally demonstrate the relationship between mechanical work and heat with mathematical precision. Joule designed beautiful apparatus where falling weights would turn paddles in containers of water. As the weights fell, they performed mechanical work by rotating the paddles. This work stirred the water, and Joule measured the exact temperature increase that resulted. What Joule discovered was remarkable. There was a precise, unchanging relationship between the amount of mechanical work performed and the amount of heat generated. The same amount of work always produced the same amount of temperature increase in the same amount of water. This meant that mechanical energy and heat energy were not separate phenomena, but rather different forms of the same fundamental quantity. Imagine the significance of this realization. Joule was demonstrating that the organized motion of his falling weights could be converted into the disorganized motion of water molecules with perfect mathematical precision. He was watching macroscopic motion become microscopic motion, seeing the connection between the visible mechanical world and the invisible molecular world. This insight opened the door to understanding heat as we know it today. Heat isn't a mysterious fluid that flows between objects. It's simply the kinetic energy of molecular motion. When you rub your hands together, you're not squeezing out caloric. You're converting the organized motion of your hands into the random motion of molecules in your skin. When Rumford's boring tools generated heat, they were transforming the mechanical energy of rotation into increased molecular vibration in the metal. The implications of this understanding extended far beyond explaining heat. It led to the development of thermodynamics, one of the most powerful and fundamental branches of physics. Scientists realized that energy could neither be created nor destroyed, only transformed from one form to another. The same energy that powers your muscles could become heat, electricity, light, or any other form of energy, but the total amount always remained constant. This principle, the conservation of energy, revealed that the universe operates like a vast, complex machine where energy continuously transforms but never disappears. The chemical energy in the food you ate for dinner could become the mechanical energy of your heartbeat, the electrical energy of your brain activity, the heat energy that maintains your body temperature, or the acoustic energy of your voice. All of these are simply different manifestations of the same underlying quantity. But perhaps the most beautiful aspect of this historical journey is how it illustrates the self-correcting nature of scientific understanding. For over 2 millennia, humans held an incorrect but reasonable theory about heat. This theory guided research, suggested experiments, and helped organize human knowledge about thermal phenomena. Even though it was ultimately wrong, caloric theory was a necessary step in the development of our understanding. The replacement of caloric theory with the kinetic theory of heat wasn't just a simple correction of error. It was a fundamental shift in how humans conceived of reality itself. We moved from thinking of heat as a thing to understanding it as a process, from seeing it as a substance to recognizing it as motion. This shift in perspective opened up entirely new ways of thinking about energy, motion, and the relationship between the macroscopic world we can see and the microscopic world that underlies everything. Consider how this historical journey mirrors the process of personal discovery and learning. Often, our initial understanding of complex phenomena is necessarily simplified, perhaps even incorrect in important ways. But these early understandings aren't failures. They're stepping stones that allow us to gradually build more complete and accurate pictures of reality. The ancient Greeks' four-element theory wasn't simply wrong. It was an early attempt to organize observations about the world into a coherent framework. Caloric theory wasn't merely mistaken. It was a sophisticated effort to explain thermal phenomena using the best available evidence and reasoning. Each stage of understanding built upon the previous stages, creating the foundation for deeper insights. This same process continues today. Our current understanding of heat, as molecular motion, is vastly more accurate and useful than caloric theory, but it's likely not the final word. As we probe deeper into quantum mechanics, explore the behavior of matter at extreme temperatures, and investigate the relationship between information and energy, new insights will undoubtedly emerge that refine or even transform our current understanding. The story of heat teaches us something profound about the nature of knowledge itself. Understanding doesn't arrive all at once, complete and perfect. It grows gradually, through the accumulated efforts of countless curious minds, each building upon the work of those who came before. Every question answered reveals new questions to explore. Every mystery solved illuminates new mysteries to investigate. As you rest there in the warmth of your current understanding, surrounded by the invisible dance of molecules that creates your thermal comfort, you're participating in this ongoing story of discovery. The sensation of warmth you feel represents not just molecular motion, but the culmination of centuries of human curiosity and investigation. You're experiencing the fruits of a long journey, from ancient fire worship to modern thermodynamics, from mystical heat substances to elegant mathematical relationships. And this journey of understanding continues. Even now, researchers are exploring how heat behaves in quantum systems, how thermal energy might be manipulated in new ways, how the relationship between information and energy might lead to revolutionary technologies. The story that began with ancient philosophers wondering about fire continues with modern scientists probing the deepest mysteries of energy and motion. In this gentle evening moment, as you contemplate the long path that led to our current understanding of heat, remember that you are part of this continuing story. Your curiosity about the world around you, your wonder at the hidden processes that shape your daily experience, connects you to every human who has ever gazed at fire and wondered what heat really is. As our evening journey continues into the deeper mysteries of heat, we find ourselves approaching the edge of the familiar world and stepping into a realm so small, so strange, and so fundamentally different from our everyday experience that it challenges our most basic intuitions about reality itself. We're about to explore how heat behaves when we zoom in far enough to see individual atoms and molecules, where the smooth, continuous flow of thermal energy that we experience in our macroscopic world reveals itself to be made up of discrete, quantum-sized packets of energy. Let's begin by imagining that we could somehow shrink ourselves down, not just to molecular size, as we did earlier, but even smaller, down to the scale where we could observe individual atoms vibrating in their positions within a crystal lattice. What we would discover in this quantum realm would seem almost magical compared to the classical world of our normal experience. Picture a perfect crystal of table salt, sodium chloride, at the atomic level. In our everyday experience, we would describe such a crystal as having a uniform temperature throughout. If we measured it with a thermometer, we'd get a single, consistent reading. But in the quantum realm, something far more subtle and beautiful is occurring. Each individual atom in the crystal is vibrating about its equilibrium position, but these vibrations aren't random or chaotic in the way we might expect. Instead, they're organized into collective oscillations called phonons, quantum packets of vibrational energy that behave almost like particles as they move through the crystal lattice. These phonons are the quantum mechanical description of heat in solid materials. Think of it this way. Imagine a vast stadium filled with thousands of people, all holding hands in a connected network. If someone at one end of the stadium starts a wave motion by moving their arms up and down, that motion can travel across the entire stadium as each person in turn lifts and lowers their arms. The wave itself becomes a kind of entity, carrying energy from one side of the stadium to the other, even though the individual people remain in their seats. Phonons work similarly in crystalline materials. Individual atoms remain bound to their positions in the crystal lattice, but waves of vibrational motion can travel through the material, carrying thermal energy from one region to another. These waves are quantized. They can only exist in specific discrete energy levels, not in arbitrary amounts. Heat in the quantum realm doesn't flow smoothly like water, but rather moves in tiny, indivisible packets of vibrational energy. This quantum nature of heat becomes even more fascinating when we consider gases, where individual molecules are free to move about. In the classical description we explored earlier, we said that the temperature of a gas represents the average kinetic energy of its molecules. But quantum mechanics reveals that even this kinetic energy is quantized. Molecules can only have certain specific energy levels, like climbers on a ladder who can stand on one rung or another but never between rungs. The fascinating consequence of this quantization is that at very low temperatures, strange and beautiful phenomena begin to emerge. As a gas cools down, more and more molecules settle into the lowest available energy states. At sufficiently low temperatures, something remarkable can happen. All the molecules can condense into the same quantum state, forming what's called a Bose-Einstein condensate. In this exotic state of matter, thousands or even millions of individual atoms begin behaving as if they were a single giant quantum object. They lose their individual identities and merge into a collective quantum entity that exhibits properties impossible in our everyday world. Heat, in this regime, becomes something far stranger and more subtle than simple molecular motion, but you don't need to cool gases to nearly absolute zero to see quantum effects in thermal phenomena. Even at room temperature, quantum mechanics plays a crucial role in determining how heat moves through different materials and how thermal energy is stored and released. Consider the heat capacity of different materials, their ability to store thermal energy. In the classical view, we might expect that all materials would store heat energy in the same way, with temperature increasing proportionally to the amount of energy added. But quantum mechanics reveals that this isn't the case at all. Different materials have different quantum energy level structures, and these structures determine how efficiently they can store thermal energy. Some materials have many closely spaced energy levels that can be easily accessed by thermal energy at room temperature. These materials tend to have high heat capacities. They can absorb large amounts of heat energy with relatively small temperature increases. Other materials have widely spaced energy levels that are difficult to access with normal thermal energy. These materials tend to have low heat capacities. Adding thermal energy causes their temperature to rise quickly because there are few available energy states to store that energy. This quantum understanding of heat capacity explains many puzzling observations about different materials. Why does water have such an unusually high heat capacity, making it excellent for storing thermal energy in heating systems and helping to moderate Earth's climate? The answer lies in the complex quantum structure of water molecules, with their multiple vibrational and rotational energy levels that can efficiently store thermal energy. Why do metals generally conduct heat so efficiently, while ceramics of similar density do not? The quantum structure of metallic bonding creates what's called a sea of electrons that can move freely through the material, carrying thermal energy much more efficiently than the localized electrons in ceramic materials. Let's take a gentle stroll through another beautiful quantum phenomenon related to heat, blackbody radiation. Every object that contains thermal energy emits electromagnetic radiation, as we explored in our discussion of radiation heat transfer. But the quantum nature of this radiation creates some of the most elegant relationships in all of physics. When you look at the glow from a piece of heated metal, perhaps the red-hot coils of an electric stove or the orange glow of a campfire ember, you're seeing quantum mechanics in action. The electromagnetic radiation being emitted doesn't come out in arbitrary amounts, but rather in discrete packets called photons. Each photon carries a specific amount of energy that depends on its frequency or color. The distribution of colors in this thermal radiation, how much red light versus orange versus yellow versus blue, follows precise quantum mechanical rules that were first understood by Max Planck in 1900. Planck's work on blackbody radiation was actually one of the founding discoveries of quantum mechanics, born from his attempts to understand the thermal radiation from heated objects. What Planck discovered was that thermal radiation could only be emitted or absorbed in discrete energy packets, not in arbitrary amounts. This quantization of electromagnetic energy was so revolutionary that it led to an entirely new understanding of the relationship between matter and energy, ultimately giving birth to quantum mechanics itself. This quantum nature of thermal radiation has profound implications that extend far beyond heated metal coils. The cosmic microwave background radiation that fills all of space, the afterglow of the Big Bang itself, is a perfect example of blackbody radiation, and its precise quantum characteristics provide our most detailed information about the early universe. Even more remarkably, the quantum nature of thermal radiation sets fundamental limits on the efficiency of heat engines and determines the maximum amount of work that can be extracted from thermal energy. These quantum limits govern everything from power plants to car engines to the biological processes that power life itself. But perhaps the most profound quantum aspect of heat relates to the concept of entropy and information. In the quantum realm, thermal energy and information become intimately connected in ways that seem almost mystical from our everyday perspective. Every quantum system contains what physicists call quantum information, precise details about the quantum states of all its particles. When thermal energy flows between quantum systems, this information can become scrambled or entangled in ways that have no classical analog. The increase in entropy that accompanies heat flow is actually a measure of how much quantum information becomes inaccessible or scrambled in the process. This connection between thermal energy and quantum information has led to some of the most cutting-edge research in modern physics. Scientists are exploring how quantum computers might manipulate thermal energy in fundamentally new ways, how quantum entanglement might enable more efficient heat engines, and how the flow of thermal energy might actually be used to perform quantum computations. There's even research into quantum heat engines that operate according to purely quantum mechanical principles, potentially achieving efficiencies impossible in classical systems. These devices might someday revolutionize how we generate and use energy. all based on manipulating the quantum nature of thermal phenomena. As you rest there in your comfortable listening space, surrounded by the gentle warmth of your environment, consider that you're experiencing the macroscopic manifestation of incredibly complex quantum processes. Every sensation of heat you feel represents the collective behavior of countless quantum systems, atoms vibrating in quantized energy levels, electrons moving through quantum energy bands, photons being emitted and absorbed in discrete packets. The thermal comfort of your body temperature represents a delicate quantum mechanical balance maintained by biological systems that operate at the interface between the classical and quantum worlds. Your cellular metabolism involves quantum chemical reactions that convert stored energy into the thermal motion necessary for life. The very consciousness that allows you to contemplate these ideas emerges from quantum processes in your brain that depend on precise thermal regulation. And yet, despite the quantum complexity underlying all thermal phenomena, you experience heat as something smooth, continuous, and comfortingly familiar. This is one of the most beautiful aspects of how quantum mechanics relates to our everyday world. The underlying reality is strange and wonderful, but it gives rise to the familiar thermal experiences that make life comfortable and possible. In the quantum realm, heat reveals itself not as simple molecular motion, but as a rich tapestry of quantized energy. Levels, discrete particle interactions, and information-theoretic processes that connect thermal phenomena to the deepest mysteries of physics itself. As you drift towards sleep, warmed by quantum processes that span from the molecular machinery of your cells to the nuclear fusion in distant stars, you're intimately connected to some of the most profound and beautiful aspects of reality. As we continue our gentle exploration through the realm of thermal energy, let's lift our gaze from the quantum whispers of individual atoms and molecules to contemplate heat on the grandest possible scale. Tonight, we'll discover how the simple phenomenon of molecular motion that warms your skin connects you to the largest structures in the universe, to the birth and death of stars, and to the ultimate fate of all existence itself. Picture yourself stepping outside on a clear night, looking up at the vast tapestry of stars scattered across the darkness. Each pinpoint of light you see represents a colossal nuclear furnace, burning at temperatures that dwarf anything we experience on Earth. Yet the warmth you feel from these distant suns follows exactly the same principles as the heat from a candle flame or the thermal comfort of your own body temperature. Let's begin our cosmic journey by contemplating our own star, the Sun, whose thermal energy makes all life on Earth possible. Deep in the solar core, at temperatures exceeding 15 million degrees Celsius, hydrogen nuclei are moving so rapidly that they overcome their mutual electrical repulsion and fuse together to form helium. This nuclear fusion process converts a tiny amount of matter directly into energy, following Einstein's famous equation E equal to mc2. The energy released by each fusion reaction is initially in the form of extremely high-energy photons, packets of electromagnetic radiation with temperatures far beyond anything that could exist on planetary surfaces. But these photons don't simply stream directly from the core to the surface and out into space. Instead, they begin an extraordinary journey that illustrates the cosmic importance of heat transfer. As these energetic photons attempt to travel outward from the Sun's core, they constantly collide with the dense plasma of electrons and nuclei that make up the solar interior. Each collision absorbs the photon and re-emits it in a random direction, often at a slightly lower energy. This process of absorption and re-emission happens countless billions of times as the energy slowly works its way toward the surface. Imagine a photon of energy that begins its journey in the Sun's core today. That photon will bounce randomly through the solar interior for an average of about 100,000 years before finally reaching the surface and streaming out into space. The fusion energy powering the sunlight that warms your face this afternoon actually began its journey from the solar core around the time the first modern humans were developing language and art. This immense journey from the Sun's core to its surface is governed entirely by heat transfer processes. Radiation, convection, and conduction all play roles in transporting the nuclear energy outward. The same fundamental principles that govern how heat moves through your coffee cup or warms your hands by a fireplace also govern how stellar energy travels through hundreds of thousands of miles of plasma to eventually reach Earth. But our Sun is just one ordinary star among hundreds of billions in our galaxy, and our galaxy is just one among hundreds of billions of galaxies in the observable universe. Each of these stars represents a massive heat engine, converting matter into energy through nuclear fusion and radiating that energy into space. The universe is filled with an almost incomprehensible amount of thermal energy, all following the same basic principles we've been exploring. Let's imagine the thermal history of the universe itself, beginning with the Big Bang approximately 13.8 billion years ago. In the first instance after the Big Bang, the entire observable universe was compressed into a region smaller than a subatomic particle, with temperatures exceeding trillions of degrees. At these extreme temperatures, normal matter as we know it couldn't exist. Not even individual protons and neutrons could hold together. As the universe expanded and cooled, thermal energy gradually allowed more complex structures to form. First, the fundamental particles could combine into protons and neutrons. Then, as temperatures dropped further, these particles could stick together to form the nuclei of the lightest elements: hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, was entirely governed by the relationship between thermal energy and nuclear binding energies. For nearly 400,000 years after the Big Bang, the universe remained too hot for atoms to form. Electrons couldn't remain bound to nuclei because thermal collisions would immediately knock them free. But as the cosmic temperature dropped below about 3,000 degrees Celsius, something beautiful happened. Electrons could finally bind to nuclei to form the first atoms. This moment, called recombination, transformed the universe from an opaque plasma to a transparent gas, allowing light to travel freely through space for the first time. The thermal radiation that filled the universe at that moment is still traveling through space today, though it has been stretched and cooled by cosmic expansion to a temperature of just 2.7 degrees above absolute zero. This cosmic microwave background radiation is literally the afterglow of creation itself, and we can detect it with sensitive radio telescopes. You're bathed in this ancient thermal radiation right now. It's streaming through your body as you listen to these words, connecting you directly to the moment when the universe first became transparent. As the universe continued to expand and cool, gravity began to overcome thermal pressure in certain regions, allowing the first stars to form. These early stars were massive, hot, and short-lived, burning their nuclear fuel rapidly and dying in spectacular supernova explosions. But their brief lives were crucial for cosmic evolution, because the extreme temperatures and pressures in their cores allowed nuclear fusion to create heavier elements: carbon, oxygen, silicon, iron, and all the other elements necessary for planets and life. When these massive stars exploded, they scattered these newly created elements throughout space, enriching the cosmos with the raw materials for planets, atmospheres, and eventually living organisms. The carbon in your body, the oxygen you breathe, the calcium in your bones, all of these elements were forged in the nuclear furnaces of ancient stars and distributed through space by thermal processes driven by stellar evolution. This cosmic recycling process, powered entirely by thermal energy and heat transfer, has been ongoing for billions of years. Stars are born from cool clouds of gas and dust that gravitationally collapse and heat up until nuclear fusion ignites. They spend most of their lives in thermal equilibrium, with the outward pressure from nuclear energy exactly balancing the inward pull of gravity. When their fuel is exhausted, they either explode as supernovae or collapse into white dwarfs, neutron stars, or black holes, releasing their remaining thermal energy in various spectacular ways. Our own solar system formed from the gravitational collapse of one such enriched cloud of gas and dust about 4.6 billion years ago. As this cloud contracted, gravitational potential energy converted to thermal energy, heating the material until nuclear fusion ignited in the central condensation that became our Sun. The same heating process that formed the Sun also created the thermal conditions that allowed planets to form from the remaining material. Earth's early history was dominated by thermal processes. The young planet was initially molten, heated by the energy of formation, and by radioactive decay of unstable isotopes inherited from ancient stellar explosions. As Earth gradually cooled, thermal energy transfer allowed the formation of a solid crust, the condensation of water vapor into oceans, and the development of atmospheric circulation patterns that could support the emergence of life. Even today, thermal processes within Earth continue to shape our planet's surface and climate. Heat from radioactive decay in Earth's interior drives plate tectonics, the movement of continental plates that creates mountains, ocean basins, and volcanic activity. The thermal energy stored in Earth's oceans helps regulate global climate, while atmospheric circulation patterns driven by solar heating distribute thermal energy around the planet and create our weather systems. But perhaps the most remarkable thermal story in cosmic history is the emergence of life itself. Living organisms are essentially sophisticated heat engines that extract energy from their environment and use it to maintain the complex, organized structures necessary for reproduction, growth, and evolution. Every biological process, from photosynthesis to cellular respiration to the electrical activity of nervous systems, involves the careful management of thermal energy. Photosynthesis, the process that powers most life on Earth, is fundamentally a thermal phenomenon. Plants absorb solar radiation and use its energy to drive chemical reactions that convert carbon dioxide and water into organic molecules. This process captures thermal energy from the sun and stores it in chemical form, creating the foundation for virtually all food webs on our planet. When you eat food, your body's metabolism reverses this process, breaking down organic molecules and releasing their stored solar energy as heat to maintain your body temperature and power your cellular machinery. In a very real sense, the warmth of your body represents concentrated sunlight, thermal energy that traveled 93 million miles through space and was captured and stored by living organisms before being released again to sustain your life. This connection between life and thermal energy extends to the largest scales of biological organization. Ecosystems are essentially networks for capturing, storing, and transferring thermal energy. Climate patterns driven by thermal energy transport determine where different types of life can exist. The entire biosphere represents a thin layer of our planet where thermal conditions are just right for the complex chemistry of life to persist. Looking toward the future, thermal processes will continue to shape the universe's evolution. Our sun will gradually grow hotter as it ages, eventually making Earth uninhabitable in about 1 billion years. After another 4 billion years, the sun will exhaust its nuclear fuel and expand into a red giant star, briefly illuminating the solar system with intense thermal radiation before cooling into a white dwarf. On even longer timescales, the universe itself faces an ultimate thermal destiny. As cosmic expansion continues, stars will eventually exhaust their fuel supplies and die out. The universe will grow darker and colder as thermal energy becomes increasingly spread out and diluted. In the far future, thermal processes may lead to the evaporation of black holes through Hawking radiation, leaving behind a universe filled only with elementary particles and electromagnetic radiation, gradually cooling toward absolute zero. This cosmic thermal history, from the Big Bang's extreme heat to the eventual heat death of the universe, provides the context for understanding heat not just as a physical phenomenon, but as a fundamental driver of cosmic evolution. Every thermal process you experience in your daily life connects you to this grand narrative of cosmic heating and cooling that spans nearly 14 billion years. As you rest there, warmed by thermal processes that connect the nuclear fusion in your cells to the fusion in the sun's core, remember that you're participating in a cosmic story of energy transformation that began with the Big Bang itself. The heat that maintains your life represents a temporary organization of energy in a universe that's slowly trending toward thermal equilibrium, toward a state where all energy is evenly distributed and no more work can be performed. But this ultimate thermal destiny is unimaginably far in the future. For now, we live in a universe rich with thermal gradients, with temperature differences that drive the complex processes of stellar evolution, planetary formation, and biological life. The warmth you feel is a reminder that we exist in a remarkable epoch when the universe is old enough for complexity to emerge, yet young enough for thermal energy to power the magnificent diversity of phenomena we observe in the cosmos around us. In this cosmic perspective, your body temperature, your thermal comfort, and your very existence represent extraordinary achievements of organization and complexity emerging from the fundamental thermal processes that govern all of reality. As you drift towards sleep, you're cooled and warmed by the same forces that shape galaxies, birth stars, and drive the grand evolution of the universe itself. As our evening exploration draws toward its gentle conclusion, let's turn our attention to perhaps the most fascinating application of thermal principles in all of nature, the emergence and maintenance of life itself. Tonight, we'll discover how every living thing, from the smallest bacterium to the most complex ecosystem, represents a remarkable thermal engine that captures, transforms, and manages energy with an elegance that surpasses any human-made machine. The story of life and heat begins with a beautiful paradox. Living organisms seem to violate one of the most fundamental trends in the universe: the tendency toward increasing entropy, toward thermal equilibrium, toward the even distribution of energy. Life creates and maintains incredible organization and complexity in a universe that generally favors disorder and randomness. How is this possible? The answer lies in understanding that living systems are what physicists call open systems. They constantly exchange energy and matter with their environment. While the universe as a whole moves toward greater entropy, living organisms can maintain and even increase their internal organization by consuming energy from their surroundings and exporting entropy in the form of waste heat and other byproducts. Picture a single cell, perhaps one of the trillions that make up your body right now. This microscopic entity is essentially a sophisticated thermal engine that operates on principles remarkably similar to those governing steam engines and automobile motors. The cell takes in high-quality energy in the form of glucose and oxygen, performs useful work to maintain its structure and function, and exports low-quality energy in the form of heat, carbon dioxide, and other waste products. But unlike human-made engines, biological cells achieve this energy conversion with remarkable efficiency and at temperatures that allow delicate biological molecules to remain stable. Your cellular machinery operates in a narrow temperature range around 98.6 degrees Fahrenheit, using thermal energy with a precision that engineers can only dream of achieving. Let's take a gentle stroll through the molecular machinery that makes this possible. Inside each of your cells, thousands of specialized protein molecules called enzymes facilitate the chemical reactions necessary for life. These enzymes work by providing thermal energy to reactant molecules in precisely controlled ways, lowering the activation barriers that prevent spontaneous chemical reactions. Think of an enzyme as a sophisticated molecular matchmaker that brings reactant molecules together at just the right orientation and provides just the right amount of thermal energy to allow beneficial reactions to proceed. Without enzymes, the chemical reactions necessary for life would either require prohibitively high temperatures that would destroy biological molecules, or would proceed so slowly that life as we know it would be impossible. This enzymatic control of thermal energy allows living cells to perform chemistry that seems almost magical. At the modest temperature of your body, cells can break apart complex molecules, build new structures, repair damage, replicate genetic material, and perform countless other chemical transformations that would require extreme conditions in a laboratory setting. The energy that powers these cellular processes ultimately comes from the sun, but through a beautiful series of thermal transformations that span multiple levels of biological organization. Photosynthesis in plants captures solar radiation and uses its energy to drive chemical reactions that store energy in the form of glucose and other organic molecules. This process is fundamentally a thermal phenomenon. Plants are sophisticated solar collectors that convert electromagnetic radiation into chemical energy. When you eat plants, or when you eat animals that have eaten plants, your digestive system breaks down these organic molecules and your cells use the released energy to power their own thermal engines. The metabolism in your cells combines these food molecules with oxygen, releasing the stored solar energy as heat and using some of it to drive the chemical reactions necessary for life. This means that every calorie of food you consume represents concentrated sunlight, thermal energy that has been captured and stored by living systems and is now being released to power your own biological processes. The warmth of your body, the electrical activity of your nervous system, the mechanical work of your muscles. All of these represent transformations of solar energy that may have been captured by a plant just days or weeks ago. Your body's thermal regulation system represents one of the most sophisticated temperature control mechanisms in nature. Unlike simple physical systems that gradually equilibrate with their environment, your body actively maintains a constant internal temperature despite wide variations in external conditions and internal heat production. This thermal homeostasis requires a complex network of sensors, feedback mechanisms, and control systems that rival the most advanced human-made thermostats. Temperature sensors in your skin, your core organs, and your brain constantly monitor thermal conditions and trigger appropriate responses to maintain thermal balance. When your body temperature begins to rise, blood vessels near your skin dilate to increase heat loss through radiation and convection. Sweat glands activate to provide cooling through evaporation. Your metabolism may slow slightly to reduce internal heat production. When your body temperature starts to drop, blood vessels constrict to conserve heat. Muscles may begin to shiver to generate additional thermal energy through mechanical work, and your metabolism may increase to produce more internal heat. All of these responses happen automatically, without conscious thought, representing the operation of thermal control systems that have been refined through millions of years of evolutionary development. Your thermal comfort right now, as you listen to these words, depends on this remarkable biological machinery operating flawlessly in the background of your awareness. But thermal regulation in living systems extends far beyond individual organisms to encompass entire ecosystems and the global biosphere itself. Forests, grasslands, coral reefs, and other ecosystems represent complex thermal systems that capture solar energy, distribute it through food webs, and eventually release it back to the environment as waste heat. Consider a forest on a warm summer day. The trees are capturing solar radiation through photosynthesis, storing some of it as chemical energy in wood, leaves, and other tissues. Some of this energy flows through the ecosystem as herbivores eat plants, carnivores eat herbivores, and decomposers break down dead organic matter. At each step in these food webs, useful work is performed and waste heat is generated, gradually dissipating the original solar energy back to the environment. The forest also creates its own thermal microclimate through transpiration, the evaporation of water from leaf surfaces. This process cools the forest interior and creates local weather patterns that affect the larger regional climate. The thermal properties of forests and other ecosystems play crucial roles in regulating Earth's overall thermal balance and climate systems. Ocean ecosystems represent some of the most important thermal systems on our planet. The vast thermal capacity of seawater helps moderate global climate by storing and releasing enormous amounts of thermal energy as seasons change and currents redistribute heat around the globe. Marine food webs, from microscopic plankton to massive whales, represent complex networks for capturing and transforming solar energy in aquatic environments. Even more remarkably, some ecosystems have evolved around thermal energy sources that have nothing to do with sunlight. Deep-sea hydrothermal vents create oases of life in the abyssal depths of the ocean, powered entirely by thermal energy from Earth's interior. Bacteria around these vents use chemical reactions driven by heat and mineral-rich water to create organic molecules, forming the base of food webs that support unique communities of animals found nowhere else on Earth. These vent ecosystems demonstrate that life can exploit thermal energy gradients wherever they exist, not just the temperature difference between the sun and space that powers most surface ecosystems. The principle is the same. Living systems position themselves at interfaces between regions of high and low thermal energy and use these gradients to drive the chemical processes necessary for life. The evolution of thermal regulation has been one of the major drivers of biological complexity throughout Earth's history. Early life forms were probably limited to narrow ranges of temperature and environmental conditions. The development of more sophisticated thermal regulation mechanisms allowed organisms to colonize new environments, from hot springs to polar regions to the upper atmosphere. Warm-blooded animals represent a particularly remarkable evolutionary innovation in thermal regulation. By generating and maintaining their own internal heat, mammals and birds freed themselves from dependence on external thermal conditions and gained access to ecological niches unavailable to cold-blooded organisms. The thermal control systems that maintain your body temperature represent millions of years of evolutionary refinement of biological thermal engineering. But perhaps the most profound connection between heat and life lies in the role of thermal energy in evolution itself. The genetic variations that drive evolutionary change often arise from thermal effects on DNA replication and repair. The metabolic processes that determine an organism's fitness in different environments are fundamentally thermal phenomena. The selective pressures that shape evolutionary outcomes often relate to thermal efficiency and thermal tolerance. In a very real sense, evolution represents a process of thermal optimization, with natural selection favoring organisms that can most effectively capture, transform, and manage thermal energy in their particular environmental niches. The incredible diversity of life on Earth reflects millions of different solutions to the fundamental challenge of building and maintaining complex organization in a universe trending toward thermal equilibrium. As you rest there, your body maintaining its thermal balance through countless unconscious adjustments, consider that you represent the current pinnacle of nearly 4 billion years of thermal evolution. Every cell in your body contains molecular machinery refined through eons of natural selection to perform thermal work with remarkable efficiency. Your consciousness itself depends on thermal processes in your brain that manage energy flow with extraordinary precision. The warmth you feel is not just physical comfort, it's the manifestation of life's victory over entropy, at least temporarily and locally. Your body temperature represents a small island of organization and complexity, maintained against the thermal trends that dominate the rest of the universe. In maintaining this thermal organization, you're participating in life's ongoing experiment with creating and sustaining complexity in an entropic cosmos. As you drift toward sleep, your body will continue its thermal regulation without any conscious effort from you. Your metabolic rate will slow slightly, your body temperature will drop a degree or two, and your thermal control systems will adjust to maintain the delicate thermal balance necessary for rest and cellular repair. Even in sleep, you remain a thermal engine, a living demonstration of how molecular motion can be organized and directed to create and sustain the miracle of life itself. As we reach the final chapter of our gentle evening journey through the realm of heat, let's settle into a contemplative space, where science meets philosophy, where the physical phenomenon of molecular motion opens windows into the deepest questions about the nature of existence itself. Tonight, we'll explore how understanding heat illuminates profound mysteries about time, entropy, consciousness, and our place in the cosmic order. The story of heat reveals something fundamental about the arrow of time itself. Unlike most physical laws, which work equally well whether time moves forward or backward, thermal processes have an inherent directionality. Heat always flows from hot to cold, never the reverse. Mixed systems spontaneously become more disordered, never more organized. This thermal asymmetry may actually be what creates our psychological experience of time's passage. Think about this remarkable fact. You can remember the past but not the future. You can influence the future but not the past, and you experience a flowing progression from moment to moment. These aspects of temporal experience may all derive from the same underlying thermal reality, the universe's evolution from the highly organized, low-entropy state of the Big Bang toward the disordered, high-entropy thermal equilibrium of the far future. Every memory you form requires your brain to increase its thermal entropy slightly. As neural connections reorganize and energy dissipates as waste heat, every decision you make involves thermal processes as your neurons fire and consume energy. The very stream of consciousness that allows you to contemplate these ideas may be intimately connected to the thermal arrow of time that governs all physical processes. This connection between thermal entropy and temporal experience suggests a profound philosophical question. Is the flow of time simply our subjective experience of living in a universe that's evolving thermally from order to disorder? Are past, present, and future just artifacts of our position in the universe's thermal history? Consider the implications. If consciousness emerges from thermal processes in the brain, and if the direction of time emerges from thermal asymmetry in the universe, then your awareness of existing in this moment may represent a unique convergence of cosmic thermal evolution and biological thermal organization. You are not just observing the universe's thermal history, you are a temporary pattern in that history, a brief eddy in the cosmic flow of energy from order to disorder. This perspective transforms how we might understand individual existence and mortality. Your life represents a temporary organization of matter and energy that maintains itself against thermal equilibrium through constant exchange with the environment. From birth to death, you're in continuous thermal communication with the rest of the universe, importing low-entropy energy in the form of food and oxygen, and exporting high-entropy waste in the form of heat and biological byproducts. When biological thermal regulation finally fails at death, the organized pattern that constitutes your physical existence dissolves back into the thermal equilibrium of the environment. But the energy that animated your life doesn't disappear. It continues its cosmic journey through endless transformations, perhaps eventually contributing to the thermal processes that will maintain other living systems in the distant future. This thermal view of mortality might seem cold and mechanical, but it actually suggests a profound form of continuity. The energy flowing through your body right now has been flowing through the universe since the Big Bang. It has powered countless stars, driven geological processes on innumerable planets, and animated countless other living beings throughout cosmic history. When it leaves your body, it will continue this eternal journey, participating in thermal processes that we can't even imagine. From this perspective, death is not the end of existence, but rather a change in how energy is organized and flows. The thermal energy that maintains your consciousness will continue existing in new forms, contributing to new patterns of organization, perhaps even animating new forms of consciousness in ways we cannot foresee. But the philosophical implications of thermal understanding extend beyond questions of time and mortality to illuminate the nature of knowledge and observation itself. Every act of measurement, every observation that gives us information about the world, requires thermal energy and generates entropy. The very process of gaining knowledge about the universe has a thermodynamic cost. When you observe something, when light reflected from an object reaches your eyes and triggers neural processes that create visual perception, thermal energy is being consumed and entropy is being generated. The information in your brain about the external world has been purchased at the price of increased thermal disorder elsewhere in the system. This suggests a deep connection between information and thermal energy that physicists are only beginning to understand. Some researchers now propose that information itself might be a fundamental feature of reality, as basic as matter and energy. In this view, the thermal processes that generate and destroy information might be as important for understanding the universe as the gravitational and electromagnetic forces that govern matter and radiation. The relationship between consciousness and thermal processes raises perhaps the most profound philosophical questions of all. Your awareness of reading these words right now depends on electrical and chemical activity in your brain that generates heat as a byproduct. The thermal energy being produced by your neural activity is quite small. Your brain uses only about 20 watts of power roughly, equivalent to a dim light bulb, but this modest energy flow somehow gives rise to the rich, subjective experience of consciousness. How does thermal molecular motion in neural tissue become subjective experience? How does the organized flow of energy through brain circuits create the feeling of being aware, of having thoughts and emotions and sensations? This hard problem of consciousness remains one of the greatest mysteries in science and philosophy, but thermal considerations provide important clues. Consciousness seems to require the brain to exist in a delicate thermal state, warm enough for rapid chemical reactions and electrical signaling, but cool enough to maintain the complex molecular structures necessary for information processing. This narrow thermal window for consciousness suggests that awareness itself might be an emergent property of matter, organized in very specific thermal conditions. Perhaps consciousness is what it feels like, from the inside, to be a highly organized thermal system that processes information about its environment. Your subjective experience of warmth, coolness, pleasure, pain, thoughts, and memories might all be different aspects of the thermal information processing occurring in your neural networks. This possibility raises fascinating questions about consciousness in other systems. Could a computer that processes information while managing thermal energy in sophisticated ways develop some form of awareness? Could ecosystems, with their complex networks of energy flow and information exchange, possess forms of consciousness we don't recognize? Could the universe itself, with its vast patterns of energy transformation and increasing entropy, be in some sense aware of its own thermal evolution? These questions push the boundaries of both science and philosophy, but they emerge naturally from taking thermal understanding seriously. If consciousness is indeed connected to thermal information processing, then awareness might be far more widespread in the universe than we typically imagine. The philosophical implications extend to questions of meaning and purpose as well. In a universe governed by thermal laws that inevitably lead toward maximum entropy and thermal equilibrium, what significance can individual existence have? If all complex organization is temporary and will eventually dissolve into thermal chaos, what meaning can our lives possess? One response is to find meaning precisely in the temporary nature of thermal organization. The fact that complex patterns like living organisms, ecosystems, and consciousness can emerge and persist for a while in a universe trending toward thermal equilibrium makes these phenomena even more remarkable, not less so. You exist as a highly improbable and beautiful thermal pattern in a cosmos that generally favors simplicity and disorder. Another perspective suggests that the emergence of consciousness and intelligence in the universe might represent something like the cosmos becoming aware of itself. Through scientific observation and philosophical reflection, the universe develops the capacity to understand its own thermal evolution, to appreciate its own beauty and complexity. Your consciousness might be one of the ways the universe experiences and contemplates its own existence. From this view, your curiosity about heat and thermal processes represents the universe's desire to understand itself. Your wonder at the connection between molecular motion and subjective experience is the cosmos marveling at its own capacity for self-organization and awareness. The warmth you feel as you listen to these words is not just thermal energy, it's the universe feeling its own aliveness. This perspective transforms thermal understanding from a merely technical subject into a profound meditation on existence itself. Every sensation of warmth or coolness connects you to fundamental questions about time, consciousness, mortality, and meaning. Every thermal exchange between your body and the environment represents a small participation in the cosmic story of energy transformation that began with the Big Bang and will continue until the universe reaches its ultimate thermal equilibrium. As you prepare for sleep, your body gradually cooling and your thermal processes slowing, you're participating in daily cycles that mirror the larger thermal rhythms of the cosmos. Your rest and renewal, like the rest and renewal of all living systems, depend on thermal processes that connect you to the deepest patterns governing reality. The philosophical fire that burns at the heart of thermal understanding illuminates questions that have puzzled human minds since we first became conscious enough to wonder about our existence. Tonight, as you drift towards sleep, warmed by molecular motion that connects you to the birth of the universe itself, remember that you are not just observing these thermal mysteries. You are one of the ways the universe has organized itself to contemplate its own beautiful, complex, and ultimately mysterious nature. And so, my wonderfully curious friends, we reach the gentle end of our evening journey through the hidden world of heat. As I sit here speaking these words into the quiet night, I find myself thinking back to that question I asked at the beginning. Where in this vast world are you listening from, and what time is it in your corner of existence? Perhaps you're still in that cozy Tokyo bedroom, where the city's thermal energy creates a warm glow against the cool night air. Maybe you're in that Irish countryside cottage, where the evening's heat is slowly radiating from stone walls that absorb the day's sunshine. Or in California, where the thermal mass of the Earth is gradually releasing the day's solar energy into the cooling atmosphere. Wherever you are, whatever time it is, I hope our exploration together has revealed something beautiful about the invisible dance of energy that surrounds and sustains your every moment. Tonight, we've discovered that heat is not a thing but a process. The joyful, ceaseless motion of molecules that connects the warmth of your skin to the nuclear fires of distant stars. We've seen how three elegant pathways, conduction, convection, and radiation, carry thermal energy through our world like streams carrying water from mountains to the sea. We've traced the long historical journey from ancient misconceptions about mysterious heat substances to our modern understanding of energy and molecular motion. We've ventured into the quantum realm where heat reveals itself as discrete packets of vibrational energy, as phonons dancing through crystal lattices and photons carrying electromagnetic radiation across the cosmos. We've taken a cosmic perspective that showed us how thermal processes have shaped the universe from the Big Bang to the present moment, creating the temperature gradients that make complexity and life possible. We've explored how living organisms, including your own body, represent sophisticated thermal engines that maintain the delicate energy balances necessary for consciousness and life. And finally, we've contemplated how heat illuminates profound questions about time, entropy, consciousness, and the very nature of existence itself. But perhaps the most beautiful discovery of our evening together is this: you are not separate from the thermal processes we've explored. You are one of them. The warmth you feel right now represents your participation in a cosmic dance of energy that has been ongoing since the universe began. Every thermal sensation connects you to fundamental forces that govern reality at every scale, from the quantum realm to the cosmic. As you settle into sleep tonight, your body will continue its remarkable thermal regulation, maintaining the precise conditions necessary for rest, repair, and dreams. Your cellular machinery will go on performing its elegant molecular choreography, converting chemical energy into the thermal motion that sustains life. Your consciousness will drift into different states as thermal and electrical processes in your brain create the mysterious phenomenon of sleep. And through it all, you'll remain connected to the grand thermal symphony of the universe, to the radiation streaming from distant stars, to the convection currents in Earth's atmosphere and oceans, to the quantum vibrations in the atoms that make up everything around you. The heat that warms you is ancient starlight, concentrated sunlight, and the echo of the Big Bang itself, all participating in the ongoing story of cosmic energy transformation. So, as you close your eyes and let sleep approach, remember that you're not just resting, you're participating in one of the universe's most beautiful thermal processes. Your sleep represents a daily cycle of cooling and warming, of energy conservation and restoration, that mirrors the larger rhythms governing everything from planetary rotation to stellar evolution. Thank you for joining me on this gentle exploration of heat and molecular motion. Thank you for bringing your curiosity and wonder to these thermal mysteries that shape every moment of existence. Thank you for being one of the ways the universe has organized itself to contemplate its own beauty and complexity. Sleep well, my friends, warmed by the knowledge that you are intimately connected to the deepest and most beautiful processes in all of nature. Rest peacefully in the embrace of thermal energy that has traveled across space and time to create this moment of comfort and consciousness, and dream sweetly of the invisible dance of molecules that continues around you and within you, sustaining the miracle of your existence in this extraordinary thermal universe. Good night, wherever you are in this cosmos of dancing energy. May your dreams be filled with the gentle warmth of understanding, and may you wake tomorrow with renewed wonder at the thermal mysteries that surround and sustain all life. Until we meet again for another evening journey into the beautiful secrets of science, rest well in the cosmic embrace of heat, light, and the endless motion of matter that makes all existence possible. The gentle sound of molecular motion continues, unheard but eternal, as consciousness fades into the thermal rhythms of sleep and dreams.